Exactly. So, thanks to Kostas, which is the coordinator of this project, we could organize this intensive course on laser physics and laser safety. Okay, thank you a lot. Thank you a lot for coming. This was very, very cute.
Thank you very much, Francesco, for organizing all the facilities and contribute to the programs. I would like to thank all of you for your time to come here and for the honor that we have to be our participants. This is the first lecture, so it's going to be quite introductory for the people that you have a degree in photonics or in lasers. So I would like to ask how many people from this room have heard anything about lasers? Oh man. So it's going to be boring. It's going to be just a reminding of the fundamentals that we are going to use later on in order to understand a little bit better.
How many people know this book?
How many do you know this book? Only few, all right? I found it. Yeah. In the bookshop.
I saw you at the one. I was there, and they told me we just sold the last one.
It was me. I was lucky.
Very good.
Anyhow, we are going to have, this is Professor Lanzani, one of the coordinators with Francesco. They are the coordinator persons from Polymy. Tomorrow, the first lecture is going to be delivered by a person that is a legend in lasers, Orancio Svelto. So I strongly suggest you to follow all of you, this kind of lecture. It's going to be very inspiring. So I go on, accelerate, because I have only 45 minutes in order to convince you and transfer you using the minimum mathematical formulas, the principles of lasers. This kind of course is developing on the frame of this project. The purpose of this project is to build a repository of online and offline materials of all the photonics science and the photonics applications. This repository is on the Moodle platform, and it will be ready in 16 months from now. Now we are building it, we are enriching this platform. By the end of 2020, we hope that we are going to have it ready and it will be used by you and your students and our colleagues in order to enrich and support the skills in photonics, the skills in soft skills. The program also envisions to build the soft skills of the scientists, like presentation skills, oral presentation skills, writing papers, critical thinking, and etc. Things that are very useful for the students, and also teaching abilities that help us to improve our teaching delivery, which is also very, very important. If we fail in teaching, we have failed as a coordinator, we have failed. Whatever knowledge we have stays to us and is not transferred to the others. So I'm going on. Laser is like an acronym of the words. I used to say that if you try to teach this course by analyzing these words, you have a full course. So we are starting with the L, which means light and electromagnetic wave, and so you have the start, you have the first chapter of your lectures. We are going to amplification by stimulate emission, which is the key process in order to build the laser oscillation and have this light with these fantastic properties, as we will see, and it's an emission device. So this is the acronymium. The first time that this has been introduced, it was quite late, in 1958. We had the first publication from Towns and Sallow, and then they just extended their research from lasers, from microwaves to lasers. This was an effort that they were doing during the research that they were doing for radars during the Second World War. So they continue their research from lasers, from microwaves to optical spectrum. And in 1960s, as we will see, we have the first building device from Ayman, a guy that he has a master in electronics and optics. Actually, it was the first application of optoelectronics, like this guy Ayman. The first time that this technology was introduced in the 1960s, it was welcomed by the scientific community as a solution without the problems. We did not have any applications. So we had something fantastic. Actually, Richard Feynman was very much wondered that why such, not a simple invention, but quite simple to realize, was not invented by, let's say, by Nazis, that they are doing so much innovative research. So the whole thing in the world will be changed. But thanks to the God, it was not invented by them. So we have now numerous applications about lasers, about heritage protection, medicine, material processing, military applications, medical applications, In science, we are using a lot. We are using lasers everywhere. And actually, you know, lasers is used everywhere now. You cannot think even one activity of your life without the use of lasers, of laser light. Think. Even if you go to the supermarket, you are using it. I mean, it's amazing. And actually, you know, they used to say that transistor as a technology has been saturated somehow, but laser applications has not been saturated. So it's something that you should invest, you should thought about lasers, and you should go on with this kind of research. Now there are two big research projects in Europe. In Photonics 21, a collaboration between universities and industry, and also a National Photonics Initiative in the States. This is like the sectors that we are using that shares the most research in lasers. You can see communication and material processing. And this is the outline of my talk. I will start very fast with the history of the laser, characteristics of the laser light, fundamental building blocks of the laser, optical amplification and broadening, the steady state condition operation, the optical oscillator, and I will finish with the longitudinal and transverse modes. I will give you the physical principles in order to know the definitions and be able to follow the rest of the courses. Okay, for the people that you have already heard this is like a repetition, and in basketball we used to say, if you learn the fundamentals, you know how to play basket. So these are the fundamentals of this intensive course. So let's go from history. These are fantastic books. As you realize, I spent a lot of money in books, and I have read all of them. The best of it is this one, How the Laser Happened. And if you read this book by Towns, who was one of the inventors, you will realize that actually laser was one of the hot subjects between the competition between the superpowers in the Cold Era war. So the Soviets and the Americans, they had the competition who is going to be the first one that is going to be who is going to introduce laser light. Actually, they had a similar competition in microelectronics. So there is a famous story from Honecker. Honecker was an East German prime minister that he was yelling, or he was fooling the Soviets that he has built the fastest transistor in order to introduce more funds. So the similar competition happened in lasers, and as you will see, in the first Nobel Prize that was awarded in laser was shared between Towns and two Soviet scientists. Yes, I'm not good in names, but you will see. So the first introduction about the simulated emission of radiation was introduced by who else? By Einstein. You will see that simulated emission is a key process in order to amplify light. So instead, we prepare our, let's say we prepare our material with optical pumping with another photons, and if this photon preserves the conservation of energy and conservation of momentum, interacts with our system that has been excited, as you will see, and then we have the emission of two similar photons. You will see the diagrams later on. So from one photon we have two photons, and this is an amplification. Of course, you know the characteristics of this light is monochromaticity, almost monochromatic. We don't have any monochromatic laser light. It's the most monochromatic light, as you will see, because there are physics laws that induce this spectral broadening, and also it is directional, and also it demonstrates temporal and spatial coherence. So then in 1953 we have these guys Charles Towns and Shallow that continue, as I told you, their work from masers to lasers. They had the first publication in 1958, and in 1958, and in 1964 they received the Nobel Prize with these two Russian guys. This is the Nobel Prize in 1964. You can see Towns shared his Nobel Prize with Basov and Prokhorov, that they were the people that they did the same research on the other part of the wall. Then we have this guy that he built the first laser. This is the first laser that the first operational laser that has been built. And the secret in order to be operational, it was that it was a pulse laser. All the people, they tried to build CW lasers, but this guy tried, you know, the pulse version. And you know, he was the first one that introduced this laser, the first operational laser in 1960s, and this is the first publication. So since then we have 14 direct Nobel Prize to laser technology. Now actually from this year we have like 14 plus 1, 15. So this year, you know, the Nobel Prize in Physics was awarded to laser physicists, actually to Gerald Mourou, Arthur Raskin, and Donna Strickland. Donna Strickland, it was the postdoc of Mourou, and they do the very good job in the pulse. He PhD student. All right. So She was very lucky. He was very lucky because obviously he was a very good student. She was a very good student. And also to Arthur Askin that he did a lot of nice work in atom trapping, if I'm not wrong. So the characteristics of the laser. This is a cartoon of the characteristics of the laser. Is the most monochromatic light. So this means that we have the emission. In simple words, if we are talking to the students, to small kids, like one color, the most distinguished green color or the most distinguished red color, it's directional. It's not like a lamp. The lamp, you know, the light is not directional. It goes, you know, all the way because of the spontaneous emission characteristics of this light. And also, you know, the laser light demonstrates very precise temporal and spatial coherence. This means that if we can determine in one point, you know, the coherence, which is a wave because it comes from the light. A light is an electromagnetic wave. If we can determine the phase in one point, we can very precisely determine at the same point after a time duration the phase. Or if we can determine the phase in one point, we can determine, you know, after a while, after a distance, you know, the phase of the other point as, you know, the wave propagates. So this kind of spatial coherence and temporal coherence provides this excellent high intensity that we can build using lasers because it's something like a parade. It's like a military parade. So if you imagine the photons that consist the electromagnetic wave that a light emits, it's like a military parade. Everything goes, you know, in the same rhythm, in the same direction. So if they apply their power, it's a very powerful tool in order to do all these processings in industry. From the other hand, the lasers that emit from LEDs, light emitting diodes, or from the lamps, you know, each photon, you know, is emitting they don't keep this coherence, and they emit also in all different directions, so the light does not acquire such a high intensity. But it's, as I said to you, you will see laser light is not is the most monochromatic light, but also is not the directional. It demonstrates a divergence angle. And this divergence angle comes as a factor of its construction and its wavelength. So imagine who has opened, the Israelis probably, they have done this. Have you ever opened a CD? If you open a CD, what you can see? A lens, because the emission facet of the semiconductor laser is around 100 microns. So it's a very small emission facet, so the light, what it's doing, is diverging very fast. And if you see, one of the characteristics of the laser light is the far field divergence angle. How fast the light is diverging, which means it's not so directional. Of course, it's much more directional than this light that illuminates in a few meters, you know, the whole room. But also the laser light, depending on the wavelength, is less directional than, you know, other light. And this is the reason why we have such a revolution of the Blu-ray compared to the CDs. Because the blue light can be focused in a very smaller spot size. So in the same dimensions of a DVD, we can scratch the DVD in smaller, in narrower, how can they say, like these mountains and valleys. And so we can store much more capacity of information. So we move from 760 megabytes to gigabytes because of this invention. And actually, that's why the Nobel Prize in 2004 was awarded to Nakamura because of the invention of the blue semiconductor laser. And as you will see, it's not the only reason. It's not only the impact of the wavelength. Actually, Nakamura, he moved from a small Japanese company, Nikkei, and then, you know, Stanford University, or, you know, in University in California, they gave him so much money in order to attract him. Santa Barbara. I have been attracted by Mediterranean University of Crete. Do you know it? A lot of money. So this is like a big impact, you know, this kind of characteristic. So another way, as I told you, the first laser was pulse laser. We have CW laser. I have my PhD in CW lasers, you know, but the majority of the people, they are doing pulse lasers. So I did my PhD in real lasers, because the real laser means that, you know, operates continuously like this one, but the most applications are coming from pulse lasers. So tomorrow you are going to listen for a lot of things about laser pulses, and you will enjoy. But with laser pulses, we don't only concentrate, you know, all the energy in short periods of time, which means the intensity is very high, because intensity is energy divided by the spot size divided by time. All right, so if you introduce all this energy within the short time, you have increased and enhanced, you know, the intensity of the light, so you have a lot of applications. However, moreover, you know, using laser pulses, you can observe, you have a very nice and very fast photo camera, which means that you can observe the duration, as you will see, of nanoworld. So iPEN was innovative photonics education for nanotechnology, and you can see in order to go to nano, you need to observe processes in nanoworld that they are very fast. So in order to capture them, you need a very fast camera, and this is provided by pulse laser. Pulse laser, in order to give a short example, is something that is on and off very fast. Okay? CW laser is something that is continuously on. All right? So you can see that, you know, the processes as we are moving to the micro world, to nano world, are getting very fast. If we move to macro world, everything is very slow. Fundamental building blocks of laser. Do we have any electronic engineers here? Very nice. Do you know the electronic amplifier? So operational amplifier. The operational amplifier consists from what? From the operational amplifier, the closed feedback loop, and this controls the gain and controls the whole device in order to have applications. So we have the gain medium, which is the semiconductor materials within the operational amplifier. We have the feedback loop in order to control this gain, and we have a fantastic device in electronics. Fantastic device. Am I right? I'm a physicist, that's why I am asking. So the same situation happens in lasers. In lasers, what do we have? In lasers, we have the material, and the material should be prepared in order to provide gain, and also we have the feedback loop in order to control the laser properties, because the feedback loop, if you think, controls the frequency that we are going to emit, provides the gain because it artificially enhances the medium length, and this is the same situation. So I used to say that this is the electronic amplifier, the same is the laser. The laser consists from the medium, and actually all the lasers they are taking its name from the medium that they are constructed. Nowadays we have lasers made from anything, from liquids, from solid state, from semiconductors, from organic semiconductors, from perovskite materials. We are using all the new materials in lasers. Actually, lasers is the first device that everything is tested, all right, and consists from the material that it has been prepared, as we will see, to have its population excited, which means to have all the electrons, you know, on the excited level compared, you know, how many electrons we have on the fundamental state, or in the low, not in the fundamental, I'm wrong, in the lower energy state. So we are selecting two energy states among the 1,000 that our atom has got. These energy states, of course, they should satisfy, they should have specific lifetimes, and they have specific properties, as we will see. So we build between two energy levels, population inversion. So which means that in the excited one has more electrons than the lower one. And this is the gain. This is the gain. The gain that our system has got, as similar as the open loop gain that our operational amplifier is characterized. Then the feedback is provided by the oscillator, and the simplest, of course this is the simplest sim of the oscillator, are two mirrors that they present reflection to the emission wavelength that our material provides. And this is one wavelength. It's not one wavelength, but let's say that it's one wavelength. So the mirrors, they should satisfy, should have 100%, not, I will ask you now, 100% reflectivity on this wavelength. And this happens, as we will see, in order to increase artificially the length of the gain medium. We will go later on to the Beers-Lambert's law, two German chemists that have changed the rule of the gain, and you will see that, you know, the gain that we can build, the gain of the closed loop, this is the open loop. The gain of the closed loop in the case of the electrical amplifier is analogous to the length of our material. But of course we cannot go to the Poland, to the Polish people that they are building the best crystals. Non-linear crystals, they are built, the best ones are the Polish in Europe. We cannot ask them to build, you know, 1 meter on 10 meters of crystal, because it's difficult to control its temperature. It's difficult to generate, to produce pure crystals in order to not introduce defects that they are going to change the energy levels. So what we are doing we are limited by the technology, and we enclose this gain material within the oscillator. So artificially, the photons, they are passing a lot of times through the medium, so they are amplified continuously. Instead to have, 2 meters, crystal that, is moving, it's getting its gain, and it will go outside, from the other end. So we have a small crystal that, the light is trapped and gets, it passes from the area of interest a lot of times. But I have a question here. Here is a 90–80%, the reflection. It is not 100%. Why? What? You need a light. Congratulations. I will show you. I will give you a pen afterwards. All right? You need a light. You need a light to make all the application. And this light, as you will see, contribute to the losses of the system. So you cannot make, this transmission like 70% in order to have a lot of light, because you are going to have a lot of losses in order the system to operate. So we will see this. So optical amplification and broadening. Let's see. So the first thing that we should do is to prepare our material in order to provide gain. If I leave you, not you, if I leave you in home, what are you going to do? Don't tell me, but what are you going to do? You would like to sleep. Everything in physics would like to stay in the lower energy level. We would like to do this. If someone was going to give us money to live, like, kings, we are going to sleep all the time. But as you can see, we are excited all the time. So in order to be excited, we spend energy. And the nature has placed everything on the fundamental state, which means in the lower energy state. So we should prepare our material in order to be excited. One way is to take cocaine, but you are not taking cocaine because it's very bad. The other thing, in the lasers, is like to use the absorption. Absorption is the first process in order to prepare our material to provide gain. Look, the last picture. From 1 photon, 2 photons. This is the gain. But first of all, we are starting from the first picture. The first picture is absorption. So we should illuminate, we should provide the extra energy to our system in order to prepare it and take the electrons on the excited state. When the electrons goes to the excited state, what do you think? It will stay forever? No. Why? Because automatically would like to return back to the sleeping mode. This is spontaneous emission, and this lasts the average amount of time that the electron stays on the excited state is how long? How long? 10 minus 9 seconds. 10 minus 9, 10 minus 10. So stays over there very shortly. What we should do now? If we leave the situation like this, we are lost. We have built what? A LED. Exactly. But in order to make a laser, and laser from LED, it has substantially differences. Laser is everything is monochromatic, directional, high coherence, temporal coherence. We can build something very powerful. With LED, we just illuminate. Traffic lights. LEDs are good for traffic lights, for BMW and Mercedes to build, their traffic lights. They are making a very pure green, very pure red, very pure blue, and etc. So we need to build a laser. So what we should do before the elapsion of these 10 minus 10 seconds in average, we illuminate, our system with another photon that has the same energy with this energy difference. E2 and E1 are the upper and the lower energy levels. If we manage to illuminate our material before the elapsion of 10 minus 10 seconds, then we have the interaction of this photon with this electron, and we have the oscillation of this electron. So the emission of similar photon with this one that introduced this transition. And we have 2 similar photons. 2 similar photons, what does it mean? 2 similar electromagnetic waves. Light. Laser, light amplification by stimulate emission of radiation. So 2 similar photons, 2 similar electromagnetic waves means the same phase, the same energy, which means the same frequency. So we have the amplification. So the only thing that we need in order to build laser, the first thing that we need is like to manage to place more electrons on the upper laser energy level than in the lower one. You can see 1, 0. This is the first thing, and this is condition is called population inversion. Of course, we are not doing population inversion by just 1 electron, because also in the laser system, as in the electronic amplifier, we have what else? losses. And we will see what are the losses. The first loss that we have introduced here is what? The output of the laser. You see, 90-80% and not 100%. So as you can see, we stimulate the emission, the light is amplified through our material. I will explain this when I'm going to reach broadening. But as you can see, that the longer the crystal, the more the gain that we can get. And this came afterwards with Beers-Laber's law, and I will show you Beers-Laber's law a little bit later. But now, forget about what are you looking over there. I just explained you the physical meaning. This is the end of the processing of what? Of the Einstein equations when they describe the stimulated emission, spontaneous emission, and absorption. So the first term over there describes how, let's say, how strong is spontaneous emission. Do we need spontaneous emission in lasers? What do you think? Do we need spontaneous emission? No. Actually, we need them. Because the stimulated emission, if I go back, is initiated by a photon. And this photon comes from spontaneous emission. That's why we cannot get the monochromatic light. This is the first reason. Because this spontaneous emission interacts with the stimulated emission that is emitted, and this somehow hammers the spatial and the temporal coherence of the electromagnetic wave, because you had the input from the spontaneous emission. So this is the first parameter, spontaneous emission. And the second parameter in denominator describes, let's keep it like this, simple, describes the stimulated emission. So in lasers we need the stimulated emission, this factor, to be the strongest one compared to what? To spontaneous emission. Am I right? So this equation over there, what does it say to us? In order to make this parameter bigger than this one, we should go to lower frequencies. Lower frequencies, longer wavelengths. That's why, you know, the red laser was introduced before the blue one, a part of the crystal stabilities. It was easier, the stimulated emission, to overcome the spontaneous emission. Also, in order to make this parameter stronger than this one, these parameters A2, B21, and B12, as you will see, is a characteristic of the material. It's generally is related with the probability, you know, this transition to happen. All right? But this parameter is a function. And it's a function of what? Of the frequency. This parameter, Ronnie, describes how much energy do we have within our, from our material, and all this energy is concentrated in one frequency. It's called the spectral density, spectral energy density. So the more monochromatic is our light, which means all the energy is focused and is included in one frequency, the stronger, the higher the value of this parameter. So what we should do, we should build somehow the energy to be emitted and be focused within this frequency. How can we do this? Also by placing the material within the cavity, because the light is passing from the medium a lot of times, stimulated. We have built population inversion, so all the time that the light is passing, you know, through the material, you know, this monochromatic light is building, because we have the stimulated emission. Remember this situation. The more the light is passing through our cavity, through our medium, you know, this effect gets higher. So 1 produces 2, 2, 4, 4, 16, and etc. All right? So we need to place, in order to build stimulated emission stronger than spontaneous emission, two things. The first one, to move to smaller frequencies, which means longer wavelengths, which means to select different energy level difference. The second one, to increase overall energy in one frequency. The most monochromatic the light is, the stronger the stimulated emission compared to spontaneous emission. But we don't have only spontaneous emission, we have absorption. Why do we have absorption? You, madam. Why do we have absorption? Who is going to tell me why do we have absorption? We have absorption because everything is sleepy, like us now. We need to excite the thing. So in order to excite the thing, to build the population inversion, to have the electrons on the upper level, we need to provide energy. All right? So we need absorption. But if our material absorbs more than it emits, it's not a laser. Light amplification by stimulate emission of radiation. Emission. We need something that emits light. So we should prepare our material in order to be more emissive than absorption. All right? So in order to do this, we need to make this parameter, which describes the stimulated emission, larger than spontaneous emission, than absorption. So what we need to do to populate the upper energy level stronger than the lower energy level. So if I go back, we don't need this situation. We are going to use this situation to move more photons, more electrons, to the upper energy level, but we need this situation. So the electron to be there. In order the electron to be there, we need the absorption. If the absorption is stronger than the emission, the absorption does not emit anything. But the stimulated emission emits, this amplified light. All right? So how are we going to do this? By population inversion. So we need, in order to be the laser, to move to smaller frequencies, it's easier, which means longer wavelengths in order to make stimulated emission higher than spontaneous emission, to concentrate all our light in one frequency, to have monochromatic light, and the third conclusion is like to achieve population inversion, to prepare our material to be excited, to be more electrons here than here. He cannot see me because he's sleepy. He's still. So, if we go now to Beers-Lambert's law, if we prepare our material, we can pass the light, and the light, if it's going to measure on the other side, we have this relationship. So output light, input light. And you can see that the output light depends on what? On this parameter, which is called cross-section. I will give you the physical meaning. And also on the difference between the upper energy state and the lower energy state, and the length of our crystal. As I told you, we cannot make crystals 10 meters long. I think now it's like around 10 millimeters, something like this, the longest one, in order to have something pure. We should make Ni1 minus Ni2 negative because we have population inversion, so minus with minus will become positive. And this has to do with the probability this transition to happen, the cross-section. It's characteristic of the material, but also from the energy pairs that we are going to select. So this changes from energy pairs to energy pairs, and changes also from material to material. All right? So artificially, what we can do? We can enhance this length, and also to build population inversion as strong as possible. This is the gain coefficient. Now, we are using our material, and we need to, how can I say, to prepare it. It's like, for men, it's like to convince a lady to go for a coffee. So you should prepare the thing. You cannot go, let's go for a coffee. No. All right? So the thing is like how many energy levels they are going to be involved. All the population, when the thing is not excited, is on the fundamental state. All right? Fundamental state is not only one state, it's all the field states, according to the quantum mechanics rules. If we cannot build population inversion with two energy states, since the one is the fundamental one. Why? Because if I go over there, at the beginning Ni2 is 0. So the material absorbs. So we excite the things and the Ni2 increases. So we are going to reach a level where Ni1 equals to Ni2. Since then, nothing happens. Because I1 equals to I2. The thing does not interact anymore. Ni1 becomes equal to Ni2. So we cannot build with a fundamental state. But if we make a trick, and this is one of the tricks of Myman, we can change the situation. And we can have 3 energy levels. So what we are doing, we're pumping our material to an excited state. All the excited state according to the Boltzmann's law, just forget if you don't know Boltzmann's law, forget it. It's a law of physics that used to say like in a simplest way that, you know, all the excited levels are empty. All right, are vacant. Everything is on the fundamental state. So if we excite our material, our electrons, they will go to an excited state number 3. They are going to relax, non-optically emitting, you know, from 3 to 2, and we are going to build a population inversion between 2 and 1. And this can be achieved. The problem with this one is like that we are trying to build population inversion between excited level 2 and the fundamental state, which means we should pump our system very hard. Why? Because we should excite to 3 at least the half of the population of the fundamental state. So which means all the population. So we should spend, it's like the electronic amplifier. We should use power supplies with a lot of voltage in order to prepare our material, to prepare our system. So we should consume a lot of energy before anything comes out. All right? So this is the first laser that was based on 3 energy levels, but was not efficient. So we moved to the new lasers that they involved, you know, 4 energy states. So the 4 energy states, they are using the trick that laser is emitted between 2 excited states. 2 excited states means vacancy. You know, since they are excited states, we have no population inversion and we can build population inversion even with 1 electron. But, you know, as you will see, they need to satisfy specific conditions. And the specific conditions are the following. We excite our system from the fundamental to an excited energy state. They stay there very briefly. On number 3, they stay the lifetime of the electrons in 3 is very short. They de-excited not luminescence from 3 to 2. And in 2, what do you think? The lifetime of 2 should be long or short? What do you think? Long. Who has said this? Yeah. Why? In order to give time to our material to build the population inversion. Population inversion refers to gain. So if we have losses, as we will see, these are the losses of the system. If we would like something to emit, we should build the material in order the gain to be built, because at the beginning we don't have population inversion. We excite, 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 we excite. We are here, the threshold. So the gain that we should provide to our system should be supported by our system. And one condition is like this energy level, the electrons to stay, you know, longer time than in 3. And when the thing relaxes, artificially, we would like to keep this gain continuously. So the lifetime in 1 should be short or long? Short, in order to throw away and always to have, you know, this kind of gain. All right? These are all the laser systems. They are built on this kind of systems. All right? Yes, sir? Excuse me?
Is it okay to ask questions?
At the end. I prefer, because I have only, I think, I don't know, I have to violate everything. So, forget about maths. This is the gain of our system. R1 and R2 are the reflectivities of our mirror. If R2, we need the transparency, we need the light to come out. I know. This R2 becomes smaller, which means the gain is smaller. And if this gain is smaller, we risk do not overcome the losses or to be a little bit far away from the losses. All right? And also we have the gain coefficient that, as you will see from the Beer's law, depends on the population inversion on the length of the cavity. And we have the losses. The losses are coming from where? Are coming from this. Are coming from defects of the crystal. If you are making long crystals, you are introducing defect, which means the energy levels are changing. You have the scattering of the emission photon within the crystal, so the photon is not reaching the output. Non-wanted absorptions in the case of the semiconductors. So the light is emitting, but then there is another energy level that absorbs this wavelength, and etc. and etc. So what you would like to do is to reach this parameter, which is the threshold, the population that you need to have in order, if the losses are here, to be there. And anything else more to be a gain, and you have a laser. So these losses, this point, which is called threshold, when you are building laser system, depends on what? Depends on the frequency. We have seen this. We have seen from Einstein that the smaller the frequency, what? The smaller the threshold. Are you coming from Columbia? I'm asking you questions now. So The other thing that is very important is this one, the cavity lifetime of the photons within the oscillator, I'm sorry. So the more the electrons, the more the photons they are trapped within the cavity, the smaller the threshold. Why? Because the losses are less, the output is less. So the cavity lifetime and the frequency are very important. The rest of them are parameters of the material and the system that we have selected. As I said we don't have the laser light, is not directional, is the most directional light, but also is not monochromatic light, is the most monochromatic light. So there are physical processes within the system that affects the lifetime of the electrons on the upper energy level. Any process that will degrade the lifetime of the electrons or the atoms on the excited state will reduce the monochromaticity of the light. All right? The first parameter that is involved is the spontaneous emission that initiates the stimulated emission. So, but the spontaneous light is there. So this degrades the coherence and the monochromaticity, the coherence of the emitted laser light. There are also other parameters like, the Heisenberg uncertainty principle. That, quantum mechanics dictates that we cannot define 100% what? The energy of a quantum system. Okay, there is an uncertainty, and since there is an uncertainty, we have this kind of okay. So if there is an uncertainty, this is the lifetime, then we have a problem. And you can see over there that what? That in pulse lasers, that everything is emitted in a short time, the uncertainty of the energy levels is like very large. It's not a monochromatic. It's a monochromatic, but it's not as monochromatic as CW lasers. You have a lot of frequencies. So we have other parameters that is like a scattering. When that we have a crystal and the crystal is on the temperature, we have the lattice oscillation. So probably a lattice oscillation will depopulate the upper energy level. And we have also other oscillations that what? They are not going to depopulate the upper energy level, but they are going to change the phase when the electron is oscillating during the transition from the upper to the lower and emit light. And this is going to change the phase. All right? We have two kinds of, this is called broadening. When you are moving from this picture, the ideal picture, to this one, this is called spectral broadening. As I told you, to keep a message, the spectral broadening, it happens because the lifetime of the electrons on the upper energy, on the upper laser energy level is somehow degraded by all these parameters, by the limited lifetime of the electrons on the upper energy level, by oscillations that they are going to knock down the electron from the upper energy state to the lower energy state, by interactions when the electron is oscillating and is emitting the light by collisions. And we have two types. How much time do I have? Two types of, I think half an hour. I have 1/4 more. No? Yeah. So they have, we have this broadening. So this broadening, forget about what are you seeing. Look at me. These are bullshitting. So the broadening, how monochromatic light we have, depends on how wide, how fat is the emission or the absorption curve. And this is characterized by full width half maximum. We have CW, like when I was doing my PhD, we were building lasers for spectroscopy, and we have CW lasers, external cavity diode lasers, that, the bandwidth of this was like less than 1 kilohertz. All right? But now, the lasers, are like many megahertz or gigahertz, depending if you are using laser pulse, the duration of the laser pulse. All right? So we have also two kinds of broadening mechanisms, the homogeneous ones and the inhomogeneous ones. The homogeneous ones, the central frequency is the same for all the atoms that they are excited. In the inhomogeneous one, these electrons and these atoms, they are characterized, a group of them, from a specific property. And they makes them distinguished from the others. All right? For example, we used to give the example of Doppler. So we have a gas lasers, and some molecules, they have a different velocity and different direction than the other one. So we are using the example of train. When the train approaches the station, the frequency is changing. Then when the train goes away from the station, the frequency changes. All right? So the same with the laser. When it emits the light, when it goes to the detector, depends on the direction and if the photon approaches the detector or the photon moves away from the detector. All right? Depends on the velocity, on the amplitude of the velocity that all these atoms they have. I will give you the questions in the exams later on. All right? So all these mechanisms contribute to move from this ideal case, monochromatic light. Are you feeling sleepy? Monochromatic light to broadening light. And this is, the function, the line shape that describes this curve. If this curve is Gaussian, the main reasons of broadening comes from inhomogeneous properties. Like we have gas lasers and we have different velocities. And when it's Lorentzian, we have all these homogeneous parameters that affect the lifetime of the electron on the excited state. Like the natural broadening, which is like it will stay there for 10 minus 10 seconds. We have the collisions that they are going to knock our electron. You remember the dual nature of light, properties, particles and waves. We have this demonstration in these systems. Like knocking the electron is de-excited, emits light. This is broadening. This is homogeneous broadening. It is described by Lorentzian shape. These are the mathematics. But the physical principle between this is like it gives the probability, it relates with the probability this transition to happen. All right? So homogeneous, this line shape, this nice curve, where is it? This nice curve could be Gaussian in the case that we have these inhomogeneous properties. We have gas lasers with different velocities. And we have, the knocking of our electron during the emission, so this changes the phase. And when we have Lorentzian, Lorentzian, yes, we have the homogeneous ones. The homogeneous ones are always there because the Heisenberg uncertainty principle is always there. The electron will never stay here on the excited state forever. After 10 minus 10 seconds, will be relaxed. And that's why this is the less monochromatic, the less spectral broadening light that we can get. Because nature dictates that the laser light is not monochromatic. The electron will stay there, not forever, but after a while, depending on our system, depending on the energy levels that we are going to select, will stay excited for a specific time. So I will skip this. Yes, we said this thing. Sorry, I said it, forget about mathematics. We said this thing. These are, a table. This is a table that describes, the different kind of broadening I have described to you by words. And, next to it, is like the mathematical formulas. All these transparencies and all the course of laser course, which is a semester course, can be accessed through the Moodle, through the iPEN project. I will send you the link in order to follow all the course, on your time. So now the system. The system is a dynamic system. We have emission, we have oscillations, and the system dynamics, let's take it there, how the time involves about the behavior of the system, what is doing. We have built our system with population inversion. So these are the losses, we are up there. We have prepared our material. Spontaneous emission initiates everything. All right, we have the oscillations, we have the emission, and then the laser, the system, the population inversion, immediately, after some microns, I think, or I don't remember, the transition, immediately, the gain, which is the population inversion, crack, goes to the threshold. Okay, we still have the emission of the laser. Look, how are you going to understand? I have laser over there, no? Everyone can see the green spot. If I'm going to measure the power, what are you going to think? The power changes? No. The power stays over there. Yeah, it depends on the battery. But let's say the battery is like the lifetime is constant. The power will be constant over there. So the intensity is constant, which means that nothing changes, nothing amplifies, nothing degrades. this means that the laser operates in a steady state. You know, the gain has been grabbed immediately to the threshold. All right? If you increase the power pumping, if you increase the pumping rate, and I switch on again the laser, you will see not 5 milliwatts, but you will see 10 milliwatts. You have prepared your material. Now the gain is not there, it's there. The whole thing initiates, but you know, after a few microns, you know, the system, the gain collapses to the threshold. You have 10 microwatts. 10 microwatts do not change, does not amplify, is not getting bigger or less, which means that everything is constant. Your gain is constant. The length is constant, the oscillator length is constant, the fucking temperature is constant, everything is constant, all right? So the system is in the steady state. So this is called saturation. You can see over there, if you increase the pumping rate, the lasing power can increase, but the threshold, pop, immediately, these are the dynamics, pop goes to the threshold. No amplification, no losses. This is a characteristic point, since you can see that initially the gain increases exponentially, but after the saturation point, if you increase, the thing increases with the length, in this case, but this is like a cartoon, but if you go to the pumping rate, you know, increases as you increase your pumping system. So let's go to oscillator, 5 more minutes. Anyhow, I'm the coordinator, I can do whatever I want. No, I'm not. Scott is the coordinator here. Cavity. The cavity, what is doing? The first thing that cavity did, enhances the length of our material. So it passes a lot of times through the neighborhood that likes. Otherwise, we should make something to start from here to the bookshop that I bought Svelto. All right? The other thing that oscillator is doing, you look at this. It traps the light within a spatial region. So increases this spectral density energy. Rho. Remember? In the Einsteins. If you don't remember, forget it. Another time, who is the physicist here? How many physics we have? Only one, me and you, and Steph and Lanzani and Lefkos. All the others, material science, electronics. Okay. We have, what do we have? The standing wave condition. What does it dictate, the standing wave condition? What does it dictate? Dictates that when we have two limits, if we have two, remember, you know, with the spring, that we have two sticks, you know, on the ground, and we attach a string. If I'm going to do with Scotoniella, we're not going to see all the frequencies, but we're going to see some frequencies to oscillate. So this means that if we have two obstacles between an electromagnetic wave or in any wave, the frequencies that they can be generated between these obstacles are dictated by a parameter. And what is this parameter? The length, the distance between these two obstacles. I gave you an example with the sticks. But in the laser cavity, where are the obstacles? The mirrors. Okay? So now we have our material. Our material, we build population inversion between these two levels, and we know the frequency of our photon is defined by this energy difference. This is one selector. But we have now, in order to build the gain, we have these mirrors also. And these mirrors, they will impose the standing wave condition. Wow. So what frequency we are going to see on the output? We are going to see the frequency that our material supports. And you know, this frequency is not monochromatic, thanks God. And the frequencies that we are going to see on the output also should satisfy what? The standing wave condition. It should support it by the cavity and also by the material. And this is the trick when we are building what? Tune-up lasers. When we build tune-up lasers, we are not changing our material, but we are tuning, placing a piezoelectric element, one of the mirrors. So we can tune the frequencies that our system emits through this selector. All right? Is it okay? So there is another problem also. So the oscillator enhances our gain because increases the length of our material. Select frequencies is a frequency selector from the frequencies that our material emits, but also we have an oscillation. So we are starting from one point and we are returning at the same point. And we have what? Electromagnetic waves. When we have electromagnetic waves, we have the phase. And in order, it's like electronic signals. If you sum two electronic signals that they have 180 degrees phase difference, what happens? Cancel each other. So we would like to secure that this does not happen within our system. So the distance, of course this is imposed by the standing wave, it's the same thing, should be such that when we have a one round trip, after one round trip, the phase of our system, the phase of our wave entrapped within the cavity should not demonstrate 180 degrees phase difference. Ideally, should demonstrate 0 degrees of phase difference or 360. Okay? Also, our configuration should trap the light within our system, because we would like to build, if the losses are here, the population inversion should take initially the gain to go upwards in order to reach a point that is higher than the losses. So if a mirror is a little bit, misaligned, after a few oscillations, the light will escape. These are losses, and you will never reach the threshold, and you will never see the lasing. So we should have a stable oscillator. Stable oscillator means satisfies after one round trip, the electromagnetic wave does demonstrate phase difference of 0 degrees and is well aligned. And you can see here that this is the criterion of stable oscillator. So D is the distance of our mirrors, R1 and R2 are the curvatures of, not the reflectivities, the curvatures of our mirrors. Why? Look the story. If you are in the water and you throw a stone within the lake, what will happen? Spherical waves are going to start to propagate, and the curvature of the spherical waves becomes from spherical to plane. So I have here my mirror. I have stimulated emission here. We have the emission of light. And the light starts like this, spherical waves, and the curvature of the emission wave starts to have a curvature, it's a wave. So we need this the radius of curvature of an electromagnetic wave when it reaches the mirror to have a perfect fit. Otherwise, if it does not have a perfect fit, you create phase differences between the each points of the different points of the wave, which means introduction of phase changes. So you need to secure the curvature of your mirror to fit with the curvature of the wave as it reaches the mirror. All right? And I will ask you something. Why do I need curved mirrors? We should use, in a very large distances, plane mirrors, because everything will become plane. Why do we use curved mirrors? Why do we use curved mirrors? No. Yes? No. No. Exactly. What is your name? Gilal. Gilal. Very good, Gilal. Yeah. Everything that it has a curvature, works like a focal length, like a lens. And the curvature and the focal point of a curved mirror, if I remember correct the things, is the half of its curvature. So everything is focused like this, and the reflection back through our material. And as you will see, I should accelerate. I will come, I think that I have the picture. Look at this. This is what it happened. The thing is emitted from our material, it moves and it contains a curvature, and this curvature, if we place here the oscillator, the mirror, this thing should fit very nicely with the curved mirror, in order to have the same phase after one round trip. So going back, I'm coming over there. So we have another definition about lasers. When you buy a laser, there are two specs, among others. One says like if it's a single mode or a multi-mode laser, and the other one is if it emits TEM00 or TEM10 or TEM11 or TEM321, whatever that means. So the single mode operation refers to how many frequencies the system of the material and the oscillator supports. All right, if these two parameters, they support to only one frequency on the emission, we have a single mode laser. This depends how well we control the losses and how we tune the frequency that we would like to emit. So longitudinal modes, if it's a single mode laser or if it's a multi-mode laser, if you see the specs, means that we have one frequency on the output, which means very monochromatic light, or we have multi-mode operation, we have more than two frequencies that they are supported by our material. Okay? So if you would like to do spectroscopy and you would like to identify this lady from all the others, you need something to have a very well discriminative properties. So you need a single mode laser to interact with this lady, an example. Okay? Then I will stay here. There is another characteristic, which is the distance. These are the frequencies that the cavity mirrors supports, and this is like our gain medium. So the frequencies that I'm going to see on the output, they should be below this curve, because this is the frequencies that my system emits, and these are the frequencies that the oscillator emits, the oscillator support. Very noisy, eh? It's like I am in the Greek basketball court, I'm shouting. Like in Yad Eliyahu, I have been in Yad Eliyahu and it was like. So we have, this distance, these frequencies that they are supported by the oscillator, they are not emitting because my system does not emit these frequencies. So the distance between two frequencies that they are supported by my material, they are called free spectral range. And the free spectral range is determined by the length of the cavity. So if you change the length of the cavity, fundamentally, what are you doing? You are changing the distance of this frequency. So I can do this. I can make smaller cavity, and I can take this frequency outside of the curve, and I will go from a multi-mode laser to single mode laser. This is the external cavity diode laser or whatever is scanning. If you place a piezoelectric material behind one of your laser mirrors and do this, probably you can go from multi-mode to single mode, depending of course on your material, how many do they support. So these are the longitudinal modes. Then, as I told you, we said about transverse modes. Wow, what is a transverse mode? This makes the things more complicated. It's not complicated. Transverse mode is like how the laser energy is distributed in the space. So over there I can see that all the energy is distributed uniformly across a small spot. But there are other systems that they distribute their energy in 2 spots, in 4 spots, and etc. Usually, when I was building laser systems, when I was moving from this spot to different spots, means one thing: bad alignment, which is accompanied by high thresholds. Other reasons is like that you have defects on your crystal. There are some dark spots, so the crystal has been burned in these regions or in this region. All right. Of course, there are. We prefer, all of us, or in my case, I was preferring TEM00 because I control everything, whenever I want. I can place a lens and concentrate all the energy wherever I want, instead to have, 2 separate spots. So, all right. And this is the last one. since I have a laser output, I want to determine how I can handle this beam. And if we are using Gaussian optics, we can do this, which means that we are very close to the optical axis. So we can predict what's going to be the spot size in a kilometer. We can predict what is the curvature, the radius of curvature of our wave in any distance that we want. We can select our parameters in order to design our pumping beam to pass through our crystals, along our crystal, and things that we can design and we can select. And these are the formulas that you can forget. So, but the meaning is like we have the capability to control the characteristics of our beam within the cavity and outside of the cavity. And with this, I think I try to give you very fast, the fundamentals of the thing. So you should keep on your mind that, we can build laser from any material now. The only thing that we want is like somehow to prepare our material in order to build population inversion, to select two energy levels that they can support the population inversion. And the one characteristic of the upper energy state should be long lifetime of the electrons. And we should emit a wavelength that is not absorbed by our material until it reaches its output. We can select the frequency of our material by selecting these energy levels, by selecting the distance of our optical oscillators, the reflectivities of our optical oscillators, the curves of our optical oscillators, and we can tune our laser system by changing the length of the cavity. So before I think I don't have time, to be honest. And I will finish here. Thank you very much. And if you have any questions, please ask me. Scott?
Yes.
Can they ask one question? Or not?
Sure.
No.
Sure.
Do you have any question? Yeah.
I will be very fast.
Yeah.
Why there were some energy levels that didn't emit light, or at least you didn't?
This is a very good question. Always I have this question on my mind, always. But the only example that I can give is like think about that there are energy levels that they are more efficient in generating phonons than photons, and you can have your example of indirect and direct bandgap semiconductors. So if you need, in order to make a transition, an assistance by a phonon, which means an oscillation from the crystal, then this is not efficient photoluminescent transition. But if a transition can happen without the assistance of a phonon, then this is high efficient photoluminescent transition. So it depends on the transition, depends on the K vector. So if the K vector, the orientation of the crystal is such that the lowest point, the highest point from where you are going to move to the lowest one is at the same orientation, it has the same K, then this transition is very highly probable, it has a high performance of photoluminescence. Okay? So if you need phonon transition, it's not efficient photoluminescence. Okay? Thank you. So